recapitulating what we have done yesterday. And so we started the Hilbert's way, so the non-intuitive one, but the one which is very, very effective through the action principle, through the variational principle. And so we started discussing particle in curved space, and we just noticed that we can actually obtain the correct action, provided we just simply replace the flat metric eta mu nu with the curved metric g mu nu. And so this leads to this minimal coupling principle, where basically people believe that reasonable physical laws can be obtained in curved spacetime, can be obtained by simply replacing eta mu nu with g mu nu, and also by replacing the partial derivatives with the covariant derivatives, so that everything is now tensorial. Of course, there was this question yesterday, whether it's related to minimal coupling in electromagnetism. Of course it is, because this is precisely what you do, right? So once you want to couple things to electromagnetism, or all you do is that you replace your partial derivative with the covariant derivative, which now has the connection, which is your U1 field, which is your Maxwell field, Maxwell for potential. So anyway, so now if we have the matter Lagrangian, so this better be a scalar. For this reason, we write here the invariant volume element, which is achieved by simply putting the square root of determinant of G. And then we require that Lm is a scalar. And so it depends on fields. And then using the minimal coupling principle, it depends on the covariant derivative of the fields. And it depends on the curve metric. And I don't know any theory where it would depend on the derivatives of the metric as well. But that actually would screw up the nice form of the Einstein equation. So anyway, so now we have this form here, and then we impose the action principle. So we vary this with respect to the field phi. And of course, we impose that this is equal to 0. Symbolically, this can be written as such. But practically, what it means is that I have to vary the Lagrangian with respect to phi, and then vary the Lagrangian with respect to the derivative of phi. And these are my corresponding Euler-Lagrange equations, where I integrated by parts using the Stokes theorem in curved space. And such thing exists, so this is fine. And these are my field equations coming from the action here. However, you can also do something crazy. You can pretend that the metric actually is dynamical for some reason. And so then you can vary this matter action also with respect to the metric. And so the result which you have to get, apart from this -1/2, which is a convention, is that, well, not really, is that if I vary with respect to the metric, I get a tensor. That tensor is necessarily symmetric because my g mu nu is symmetric. And you call this tensor an energy momentum tensor. And the statement is, if the equations of motion for the matter are satisfied, so if this guy is 0, then this tensor here will be conserved. Okay, and so people call this a conservation of the energy momentum. But actually, so you have analogy in flat space is d mu t mu nu equals to 0, and then in flat space you can show that out of this law it follows that you have conservation of energy and momentum. So conservation of energy and momentum in flat space. And so people might intuitively think is that this curved space version also means conservation of energy and momentum in curved space now. However, this is not true. And in general, this equation does not imply any conserved charges whatsoever. Okay, I will discuss why it is so, hopefully today, but if not, maybe tomorrow. But so these two are very, very different. Very different. And I would almost say that they have nothing to do with each other. Okay, so now let's first look at what this conservation equation in curved space really gives me. And so the best thing is to do it on an example. And the simplest example, which is useful, is that of a perfect fluid. So example. So what nabla mu t mu nu equals to 0 gives for a perfect fluid. And so just just to look at what this equation really means. Okay. So now for this I have to write down what the energy momentum tensor of the perfect fluid is. And the perfect fluid is something which has some velocity flowing in the space-time. It has some energy density, and there's also some isotropic pressure. Okay, and so these quantities, of course, enter the expression for this T mu nu, and the T mu nu is simply given by energy density plus pressure times 4 velocities plus pressure times the metric. So just please take for granted that this is the energy momentum tensor of a perfect fluid, and then U alpha is the 4 velocity of the fluid, and then rho is the energy density, and P is the pressure, and both these quantities are basically in the rest frame of the fluid, measured in the rest frame of the fluid. So as measured by so-called co-moving observer. Co-moving observer. That is an observer who is moving with the fluid. So the fluid has some flow in my space-time, and if I'm sitting in that flow and flowing with the fluid, then I see around myself some energy density and some pressure, and that's the physical meaning of these quantities rho and P. Okay. By the way, this is the most fundamental energy momentum tensor which you will discuss the whole cosmology. So you will basically say that our universe is simply like a perfect fluid, and that it has some energy density and there's some pressure to it. Pressure is mainly caused by radiation. So we have the universe filled with radiation that causes the pressure, but everything else has basically just energy density. Well, lambda has some pressure as well, but yeah. Okay, so this will be enough to describe our universe. Okay, so now we have this energy momentum tensor, and so in order to see what this equation gives us, let us first introduce a useful quantity, which is a projector. So let's say I have the 4 velocity flow going like this. So this is my 4 velocity u mu. And so you see that immediately the space-time splits into orthogonal spaces. One space which actually follows, which is in the direction of u mu, but there will be also another space which is orthogonal to my velocity u mu. And so I can always split the space-time at every point into something which is parallel with the 4 velocity and which is perpendicular to the velocity. Okay, so I don't know how to call this space. Let's call it just perpendicular space. So now, interestingly, if you have this 4 velocity u mu, you can always find a projector which projects any tensor into the space which is perpendicular to my 4 velocity at every point. So there's a projector to my perpendicular space, and the statement is that this projector is simply, well, it's a matrix H alpha beta, and this is given by delta alpha beta plus u alpha u beta. Okay, so that's the statement. This object is a projector to my perpendicular space, and what it means is that if I act this object on, let's say, a vector, so if I do H alpha beta on some vector v beta, what do you get is V alpha, but now this thing will have only the perpendicular part. So I really take whatever the vector I have, I just project it down to my orthogonal space. Okay, so now why is this a projector? So you know from mathematics that projector, well, so better be orthogonal to my direction U alpha. So H alpha beta times U beta. Let's check that this is 0. Well, the first term just gives me U alpha, and then the second term gives me, so I have U alpha, U beta, and then U beta. But U beta is -1. So this is U alpha minus U alpha, which is 0. So indeed, this thing, when it projects the thing, which is just really perpendicular, gives me 0. So that's what you should expect. And in order this to be a projector, it also has to satisfy that if you project twice, you get the same thing as if you project once. So that means H alpha beta, H beta gamma. And you can easily check that this gives you H alpha gamma. So it doesn't matter how many times I project, I simply get the same thing. And so these are the properties of the projector. So I have projected to my perpendicular space, but I also can form a projector which projects to my parallel space with the power velocity. And of course, the sum of these projectors better give me 1. And so then it's obvious that 1 is this delta alpha beta. This is the projector to the perpendicular space. So this must be the projector to the parallel space. To parallel space is my forward. Okay, and again. So now, so having a field in the space-time, you can decompose each and every object into these perpendicular spaces to my forward velocity and the parallel spaces to my forward velocity. Any questions to this? Yes?
Why isn't it minus of that?
Oh, it's just becomes, it's just because of this stupid normalization of the forward velocity. So this is -1. So if you had, so this is, I'm just using the fact that I have time-like geodesic. If I had space-like geodesic, which would be normalized to +1, then I would have a minus there.
No, but the projection. She's asking about the projection, because the sum should give you the delta function. So it should be minus U alpha U beta, the projection to the parallel space.
Sure. Yeah. Well, what I would just be doing anyway, I would just multiplying by U alpha. but yeah, I agree with that. So okay, so now let's have a look what this nabla mu T mu nu is. Nabla mu T mu nu. So we require that this is equal to 0. And so we have quite a few terms, right? So first term is that we differentiate this rho plus p. It's nabla mu on rho plus p, and then we leave u mu u nu. Then we differentiate the first u mu, so it's plus rho plus p nabla mu u mu u nu. Then we differentiate the second nu, so it's plus rho plus p u mu nabla mu u nu. And so then we are done with the first term, and then we differentiate nabla mu on p and g mu nu. And then finally we differentiate the metric, but we know that the metric is covariantly constant, and so that gives me 0. Okay, so this is what my conservation of the energy momentum is. And so we have all these terms here. So now let us first look at the projection of this, projection to the perpendicular space. Okay. So what it means is that I multiply this by, so multiply by h alpha nu. Okay, so this thing has only one free index nu, and now I project this index to the perpendicular space via h alpha nu. Okay, so now we have 0 equals 2. So I hit this term with h alpha nu. Of course, that means that in the end, h alpha nu hits this guy u nu, but u nu is perpendicular to, well, it's parallel to geodesic, but this is perpendicular. So this term gives me 0 because h alpha nu is hitting u nu. What about the second term? Huh?
You also have a u nu.
Exactly. So you also hit this one here, so you get another 0 here. Okay, so then I have the third term, which is rho plus p u mu. And then I would have this h alpha nu nabla mu u nu. And then I have the last term, which is plus h alpha nu nabla mu p g mu nu. Okay, so this is what I get. Now I can use my definition of what h alpha beta is. So this thing here is just delta alpha nu plus u alpha u nu. Okay, everybody agrees with this. So then look at this beautiful thing. So what happens if I act with this term on this guy? What do you think?
It's 0, right?
It's 0 because?
The derivative is perpendicular to the
Well, the answer is correct. And yeah, you can think about it like that, the acceleration is perpendicular to my fall velocity. But you know, all what it is like u nu nabla mu u nu nabla mu u nu. That's the interesting part, which is of course something like 1/2 of nabla mu of u square. But u square is -1, so if I differentiate that, I get 0. So this is 0. So this term doesn't contribute, so that term is gone. And then all is left is just delta alpha nu, which I can pull through the derivative. It's just 1 or 0, whatever. So I have it, you know, the term is 0 equals to rho plus p u mu, and then nabla mu u alpha. Okay, so that's the first term. And the second term, well, if you look at this thing here, well, this is just a gradient of p, of the pressure, but now projected to the perpendicular space. And this is just rising the index of that object. Okay, so this is, I could call this, it's a gradient of the pressure, but now you take its perpendicular part and you rise the index, and this is it. And so you obtain, so by the way, this thing here, what is this thing here?
The covariant derivative along the curve.
Exactly. So there's something like, again, the acceleration or whatever, yeah, the covariant acceleration. So you just derived the beautiful equation that rho plus p times, and let's write it, I don't know in which way, well, let's write it d u alpha over d tau. Well, it's not good. Let's write it the way we wrote it there. It's nabla u alpha equals to minus nabla p perpendicular alpha. Anybody recognizes this equation? You've studied some fluid mechanics, something like that. Anybody seen this equation before? Apart from something. So we are saying like the acceleration is given by the gradient of the pressure, and there's also the energy density here. So this is basically the most simple version of the Navier-Stokes equation. If you have like zero dissipation and stuff like that, which you always have for perfect fluid. So this is the Navier-Stokes equation. So now if I restored the units, so some people who have seen Navier-Stokes equations, they would see that there's like rho and the acceleration and the nabla p, but this term, the p, is not there. So the p term here, if you restore the units, it would actually be p over c squared. So that would be c squared here, and the second term would be really, really suppressed. And so in the non-relativistic limit, if you see Navier-Stokes equation, this term is not there. So this is the general relativistic correction, or relativistic correction. So this is the GR correction. So that's a general feature. So pressure also carries some energy density, if you want, and as such, it actually contributes. It also gravitates. So actually, if you want to establish equilibrium, typically I don't know. Let's say I have a star, and so in that star I want to have an equilibrium. So I don't want the star to be collapsing or anything. So now there's always a gravitational pressure inward, right? And so there's a gravitational force inward, which would actually make me collapse. But I can balance that with the pressure which goes outwards, right? So if I have some pressure inside the star, the pressure goes out, the gravitational force goes in, but I can have equilibrium. But in general relativity, this is much more complicated, because if I have some pressure which is balancing my gravitational attraction, this pressure also self-gravitates and actually causes bigger gravitational force. Okay, so then it's much more delicate and much more complicated in general relativity. So the pressure also gravitates in GR. So anyway, so this is the Navier-Stokes equation. And so you see that, and of course that's an equation of motion for the fluid, right? So this is a equation of motion for the fluid. So you see that whatever the conservation of the energy momentum tensor gives you is actually not a conserved charge, but rather is an equation of motion. Okay, we just got an equation of motion for our field, for our fluid, out of the conservation of energy momentum tensor. Okay, so by the way, if I do, so I still have this equation nabla mu t mu nu. So now projection, which is to the parallel space, so along the fluid. So I just multiply by u nu. So I'll have just 0 equals to u nu nabla mu t mu nu. Okay, so I'm just projecting along the flow. All right, so again, I have this equation here, but now I have to multiply by u nu. So what do I get from the first term? If I multiply by u nu,
-1.
so this guy with that guy gives me -1, and it's this thing here. So this is equal to a minus rho plus p, and then what was there? Nabla mu u mu. So that's the first term. What about the second term?
Same.
The same thing. Again, I have u nu hitting that u nu gives me -1. So it's minus rho plus p. And then what was there is u mu nabla mu. What is it? Nabla mu u mu. Nabla mu u mu. Okay. Now, what about the third term? I'm hitting this u nu at 0. So I have u nu, nabla mu u nu, which is precisely this, which is 0. So it's plus 0. And then, well, if I hit that with u nu, it just gives me u mu, so plus u mu, nabla mu acting on P. All right. So now you can group some terms together. So first of all, notice that I have nabla mu acting on P u mu, and with a minus sign, but I have the same term with a plus sign. So this term cancels this term here. And then you have this u mu nabla mu on rho equals to rho plus P times nabla mu u mu. And then this is this minus sign, so better put plus here, and equals to 0. So has anybody seen this equation? Again, provided that this term here, the pressure term, would be suppressed by c squared. And so that wouldn't be there. So is this equation familiar from the fluid mechanics? It's a continuity equation. Thank you. So this is a continuity equation. And again, you would recover the standard non-relativistic form by suppressing that P term here. So see that beauty, right? So we just start with the equation nabla mu T mu nu equals to 0, which is the conservation law for the energy momentum tensor. But we see that we not only recover something like conservation equation, something like continuity equation, which is there, but, well, not really, but also we recover the equations of motion. Okay, so nabla mu, and this is true in general, so nabla mu T mu nu sort of implies equation of motion for the matter. Well, at least in this case, but you can show that this is actually much more general. So let's say I took my action for the particle in curved space, which is just minus m d tau. I would vary this action with respect to the metric. I would find the corresponding T mu nu. That T mu nu is conserved automatically. And now I am asking what this nabla mu T mu nu equals to 0 gives me for the particle, and you would find that it gives you the geodesic equation for the particle. So actually, this thing here, you should be thinking about nabla mu T mu nu as an equation of motion for the matter. Okay. So now there was a huge debate, which lasts until now, whether this is true for any matter. So for example, for Maxwell equations. So typically what people do is that they show, well, if the Maxwell equations are satisfied, then I construct the corresponding T mu nu for the Maxwell equations, then it will be conserved. Okay, so that's easy to show. That's a couple lines calculation. However, I think there is a statement that you can also reverse that. So I have T mu nu for my Maxwell field. I impose this, and you can show that actually the Maxwell equations have to be satisfied. Okay, provided some extra conditions, but it's almost true. Okay, so you should better be thinking about this as an equation of motion. Questions? All right. So now, so 2 people voted that they want to see some NLE. So I'll just do a very brief intermezzo. So what you want to now do is that we understand how the matter evolves in the space-time, in the curved space-time. So the next step is to see, what is the equation of motion for the gravitational field itself, right? But it's actually useful to look at the electromagnetic case first. And so intermezzo, let's call it action for electromagnetism. Action for electromagnetism. All right, so let me start with something very, very simple. So if I want to write down the action for electromagnetic field, everybody knows the answer. But what I am trying to find is some scalar which would depend on my field and its first derivatives, right? Precisely as happens over there. So I want to find an action which depends on a mu and the derivative of a mu. Okay, so we want a scalar scalars that depend on, let's call it f, which is my Lagrangian for the electromagnetic field, and that will depend on my vector potential. Let's do it in flat space first. So it depends on A and the derivative of A. Okay. However, there is an extra requirement, is that I also want this thing to be gauge invariant, so that I avoid some equations of motion which are not gauge invariant. So plus you require gauge invariance. Okay, and that basically tells you that the quantity which you have to use is f mu nu, and so the only dependence on A is through f mu nu. Okay, so then you have f mu nu, which of course is a function of dA, of A and dA in general, but of dA. Okay, so gauge invariance requires that I'm using this f mu nu. So then the question is, how many scalars are there I can form out of f mu nu? Answer?
Two.
Huh? Two. Which are?
F mu nu, F mu nu.
Uh-huh.
Mu nu metric.
F mu nu metric. What does it mean? F mu nu, G mu nu?
No, you kind of no.
Aha. So you're right. Now you are right as well. So one scalar is, everybody agrees on, it's, let's put 1/4 f mu nu, f mu nu. So that's one scalar. Then there was another proposal for a scalar which would be f mu nu, eta mu nu if you are in flat space. However, the problem with this guy is that it's 0. So this is not the scalar which we are looking for, because it's symmetric times antisymmetric. But there is another scalar which was pointed out, and that's 1/4 f mu nu, and then you take the Hodge tool of f mu nu, and so that's another scalar here. Okay. So now basically, now all these things, they depend only on the first derivatives of my vector potential. So in principle, I can design any Lm, so any L, which is a function of my f and of my g, actually will give me second order Maxwell equations. Okay. So by the way, the G is actually a pseudo-scalar, so it's not a true scalar, so it doesn't respect parity. So people typically put fg square, so now this is really, so g square is really a scalar. So any Lagrangian which is of this form will give you some field equations for your Maxwell for potential. This will be second order equations, which we want. We don't want higher order equations. And they will define my electromagnetic theory. Okay, so of course, the Maxwell or linear electrodynamics is simply defined by saying that L is simply F. Okay, so that's the simplest possible choice you can do, and this is the Maxwell theory. Okay. So now, why would anybody want to do something else? And the answer is, yeah, people actually do want. So what is the problem as we discuss it? And people didn't know how to deal with that. So as we discussed in the classical physics course, we saw that if you just take, a charge, and so charge, I have charge, and then you calculate the self-energy of this charge, so it produces the field which goes like 1 over r square, and then if you calculate the corresponding energy, that energy actually blows up. So self-energy, if you calculate just E square, integrate over the volume of the space-time, then you find that this is infinite. And so people don't like this, didn't like that, of course. And so now we are talking about the times just around the special relativity invention, so around 1905. So really people didn't like this infinite self-energy. And so they said, instead of considering E as a function of r, which blows up in the origin, well, let's try to smooth it out and let's have a finite energy. And so let's make a field like this. Okay, so that it goes to a finite value instead to an infinity. And as I said, this was a time of special relativity. And so people were obsessed with this absolute velocity c. And so Born comes, and I don't know, I think it's something like 1908 or something like that. So it's like really, really after special relativity. And he says, motivated by special relativity, we know that all we have to do is that this is my old stupid Lagrangian for a particle, 1/2 mv square. And so the special relativity tells you that you should replace this with mc square 1 minus square root of 1 minus v square over c square. Okay, so this is the special relativistic version for the particle. And how you arrive at that is that the c is the absolute or the maximal velocity. Okay, so people realize actually I cannot move arbitrarily fast, and so I have this maximal speed here. Well, very good. So let's do the same thing for electromagnetism. So now my Maxwell theory tells me at r equal to 0 I have infinite electric field. Let's try to make it finite. Okay, and so the electromagnetism. So let's do first. So this invariant f is something like 1/2 e square minus b square. So it's in the static limit is just minus 1/2 e square. Well, it looks like this guy here, right? So I have an arbitrary large e, and I have arbitrary large v here, and it's quadratic in e square, and it's quadratic in v square. So this is what was the proposal for Maxwell theory, right? We were setting L equal to f, which is minus 1/2 e square in the static limit. Okay, and then so what Born said is that, well, let's write down the corresponding Lagrangian here. So the Lagrangian density would be now b square, and I'm switching the signs, but it doesn't matter. 1 minus e square over b square, square root of that, minus 1. Okay, just this direct analogy where I say b is the maximal electric field I can have in nature. So in other words, it's the value of that field at r equal to 0. So you don't go to infinity, but you go to the value p. Okay, and so we wrote this, and then of course this is valid in electrostatics, and this wouldn't, be invariant. So if I switch on the magnetic field, but if I write it in the form like that, 1 minus 1 plus 2f over b square minus 1, then now this depends on my invariant f, and this will be a scalar, and it will be a nice theory. Okay. So this is what Born wrote down, and he was really motivated by special relativity, and this is called Born electrodynamics. And it's 1908. So now you see that this thing here has some square root, and it's bloody nonlinear, right? So actually to find solutions of this theory is very, very complicated. People are trying until now. The only thing which is really known is the spherical symmetric solution. But you know, is this theory here. So then this happened, like, let's say, I think it's 1908, but don't take me for granted. So then people played with this much more in the 30s, and in particular Infeld, I think, who was Einstein's student, they looked at this in the 30s, and then they formed a nicer theory, which is known as Born-Infeld theory. So this is in 30s. And so basically what they did is that they played with, if you want, Nambu-Goto action. So they looked at determinant. So they were coupling electromagnetism to gravity, and then they came up with this interesting object to look at. So if you have determinant of the metric plus the electromagnetic field, and so if you subtract the determinant of the metric as well, again, okay, so if you do that, you find something like square root of minus g, and then square root of 1 plus f minus g squared minus 1. Okay, so now you find basically the Born electrodynamics plus some correction in terms of the other invariant. Okay, and so this is the origin of Born-Infeld theory. So now let me write down the modern version of that. So there's the corresponding Lagrangian Born-Infeld, and it's b squared, which is still the maximum value of the field. It's 1 plus 2f over b squared minus g squared over b to the 4 minus 1. Okay, so this is the Born-Infeld Lagrangian, and it's related to this determinant of g mu nu plus f mu nu. Okay. So now this was formulated in the 30s, and then, you know, again, it's bloody nonlinear, but it has finite value of the field everywhere. So you cancel many divergences, you have finite cell force, it's relativistic, it's gauge invariant, it has all the nice properties. It reduces to Maxwell field, provided that the field strength is small. If f and, you know, if f mu nu is small, then you can do the Taylor expansion, and this reduces to f for weak fields. So very, very far away from the charge, you would just recover Maxwell theory, but close to the charge, you would have the finite value. All right. So now this was in the 30s. Then people were really interested in these things in the 60s. So this thing is like Phoenix from the ashes. So in the 60s, people like Plebański, like this famous Polish relativist, was really interested in the theories of nonlinear electrodynamics. And then he showed that this is the unique theory which has nice properties. So out of all the theories which I can consider, where I take L to be any function of f and g squared, this is the nicest one of them all. In particular, it doesn't have like a birefringence phenomena that you know, the light propagates only in one direction. Typically, you have like split of lights, and they propagate different speeds, different directions. So this doesn't have that, and so on. So it's a really, really nice theory from the mathematical point of view. But so that was relativist. Okay, so 60s. I'm spending too much time on this. Sorry for that. So 60s. Is relativists were interested in this. And then in 80s, string theorists discovered this theory. String theory, and in particular, one of the examiners of your PSI essays, Rob Lee actually came up with the idea is that this is precisely this is the theory which emerges from the string theory. It's not the Maxwell theory, it's this theory here, actually. So strings and branes and whatever. And then in 2000, people discovered that this is useful for cosmology. And so this Born-Infeld type of action, this determinant of G mu nu plus F mu nu, is how the inflation is modeled and stuff like that. And so it's really, you should at least as a theorist know the name Born-Infeld. So it's an example of nonlinear electrodynamics, which, however, seems to be emerging in all the fields of theoretical physics. Questions, comments?
So in there you have a metric that doesn't have to be the flat one, right? It's a general metric.
So here, this is I'm back to curve space.
So in the Lagrangian there.
So here, I think all I have to do is that I have to put square root of G somewhere. This would be general relativistic version.
Can you measure this, like departure?
Of course, people try. So I just seen a recent article where people like gather whatever is known about the experiments measuring the nonlinear effects of electromagnetism. So certainly, if you go to quantum electrodynamics, because of the loop corrections or whatever, you can scatter photons on photons, right? So in Maxwell theory, everything is linear. So if you have one photon going this way, another photon going that way, they just pass each other and nothing happens, right? This is not true in electrodynamics. Quantum electrodynamics, they can scatter because there are loop corrections. So these things actually are much closer to the quantum electrodynamics than the Maxwell theory. In fact, there is a theory which is not exactly this one. It's called something, Heisenberg something, I don't know. So a different nonlinear electrodynamics theory, which is actually designed to model quantum electrodynamics effects classically up to, I don't know, 3 loops or something like that. And so then you have some expansions in F and G square there, and you can write down the Lagrangian, and that actually mimics classically what happens in the quantum electrodynamics. All right, enough of this. So anyway, so the take-home message is that we were trying to construct a theory which, well, the Lagrangian, which depends on A and the first derivatives of A, and we require that this is a scalar, and in the electromagnetic case, you also require that it's CKH invariant. Yes?
But you have F there.
Yeah.
That's not a scalar.
No, sorry. I define it that way. So it's F mu nu, F mu nu. I just simplified my life by saying that F is this 1 over 4 F mu nu, F mu nu.
And when you're saying that that this is a finite theory or that you obtain finite results, is it you're meaning this is renormalizable?
I haven't said anything like that. I don't know. Probably not. I don't know. This is a classical theory of electromagnetism, which is highly nonlinear. It's very difficult to find any solutions whatsoever. So apart from spherically symmetric solutions, people are trying. So by the way, your homework number 1, that's the origin of the homework number 1, is that you study the charge in the lab in the Maxwell theory, right? And so a research project would be how a charge in the lab looks in this Born-Infeld theory. Okay, so that could be a research project. However, the equations are highly nonlinear, and I wasn't able to solve it. So, and I already was trying for 10 years. So, so probably it's not a good research project. Okay. Okay, part C, Einstein-Hilbert action. And for that, all you need to find is just, the fields of uniformly accelerated charge. So it's really very simple fields in the Maxwell theory, but in this Born-Infeld theory, it's really complicated. So in order to find the action, we would like to have a scalar which depends on the metric and the derivative of the metric, right? So then if we have such a scalar, then we are guaranteed that the equations of motion will be second order differential equations for my metric. Okay? Do you see a problem? Any problem whatsoever? Can we do this? So we want a scalar quantity, something which is diffeomorphism invariant, which depends only on the metric and its first derivatives. Think about the equivalence principle. So we know that by the equivalence principle, we can always go to a freely falling frame where we can get rid of all the derivatives of the metric, or the first derivatives of the metric, right? So I can always set this to eta and this to 0, but of course, well, it doesn't matter that I can set it to equal to eta, but this will be only a function of g, right? So that will not give me second order differential equation. So this, unfortunately, this does not exist. Not exist because of the equivalence principle. Okay, so this is not the way to go. And so maybe I can actually go about doing the second derivative. So instead, we try an invariant which depends on g, dg, and d square of g. Is there such an invariant? Ricci scalar, for example, right? So e.g., so now we have an answer. Of course, it's not a unique answer. We can consider r square, r cube, r whatever, square root of r. But this would be the simplest one, and such a scalar exists. Well, hence we have the Einstein-Hilbert action. Einstein-Hilbert action, which is as Einstein-Hilbert depends on the metric, and it's okay. There is some stupid prefactor, 1/16 pi g. G is the Newton's constant, and then you have to do an invariant metric element. So d. Okay, let's do d4 of x. Square root of minus g. We are in 4 dimensions. And then you just put the Ricci scalar, which is a function of g, dg, and d square of g. Okay? But that's the simplest possible scalar I can write down. But of course, the unpleasant property of this scalar is that it also depends on 2 derivatives of the metric. But simply, I cannot do without it. I cannot do with just 1 derivative because there is no such scalar. Okay? So by the way, this is called Einstein-Hilbert action, but of course, Einstein didn't know about this action at all. It's all Hilbert's work. So historians were very nice to Einstein that actually they put Einstein here as well. Okay. Very good. So now this is our ansatz for gravitational action. And so let's vary this action and see what it gives us. And for that, we will use a dirty trick that the Ricci scalar is actually a contraction of the Ricci tensor. Everybody knows that, right? So, so when you vary this thing, is that there's a dirty trick. So there's 2 dirty tricks. Of course, the Ricci scale is a horrible function of these second order derivatives and first order derivatives of metric and so on. But one dirty trick which you have to use is that the Ricci scalar is simply g mu nu. Which way I write it? I just write it this way. Yeah, g mu nu, and then r mu nu. Okay, so it's a contraction of the Ricci tensor. And of course, we also have to use the fact that you derived in your tutorial is that delta square root of minus g is minus 1/2 square root of minus g mu nu delta g mu nu. Okay, so we will use these facts to actually vary this action. So let's do it. So delta as Einstein-Hilbert, okay, so it's 1/16 pi g, and then you have to vary these terms. So you have to vary the square root of g, you have to vary r alpha beta, and then you have to vary g alpha beta. So we have three terms which depend on the metric. Let's vary these three terms. So this is 1/16 pi g and an integral. And then the first term which we have is that we have to vary this delta square root of minus g. So that will be, the first term is r times delta square root of minus g. I just combine these two terms together again to produce r. So that's the first term. The second term is plus square root of minus g r mu nu r alpha beta delta g alpha beta. So I'm varying this guy here, and then the last term is that I have to vary this guy here. So it's plus square root of minus g g alpha beta delta r alpha beta. That's the three terms I have. Okay, so I want to write it as something times delta g alpha beta. Okay, and then whatever that something is has to be 0, and that's my equation of motion. So this term is the simplest one, and I'm done with it, right? So it's just I already have written as something times delta g alpha beta. Okay, so now this term here, well, I just use the delta trick you derived in your tutorial. And so this is minus 1/2 r square root of minus g, and then g alpha beta delta g alpha beta. That's the first term. Okay, so I varied the first term, I varied the second term. Know that these two terms, when they combine together, I can write them as minus square root of g, and then I write them as r alpha beta minus 1/2 r g alpha beta delta g alpha beta. And maybe you recognize this object here is the Einstein tensor. So this gives me g alpha beta. So the first terms combined together give you square root of minus g alpha beta delta g alpha beta. Okay, so now if you know Einstein equations in vacuum, so we are discussing you know that in vacuum you have to have g alpha beta equal to 0. So we already derived the Einstein equation. So what about this bloody last term? So this bloody last term is a lot of work. But fortunately, we don't have to do it. You will do it in your gravitational physics course. But the statement is that if you write this g alpha beta delta r alpha beta, it's actually nothing else than a total derivative of some vector v mu. This vector v mu can be written as nabla beta delta g mu beta minus g alpha beta nabla mu delta G alpha beta. Okay, so the explicit form of what V mu is not important. What is important is that the last term just gives you a total derivative. And so you can change it by Stokes' theorem to a surface integral. And so it's just a boundary term. So this is just a boundary term. And so it doesn't modify my equation of motion. So you see how simple it is to vary the Einstein-Hilbert action. All you need to know is to vary square root of G, and this is just for free. And this doesn't do anything. Okay, so if you're interested in the details, you can look them up in Volt or wait for the gravitational physics. Yes?
Is the boundary term important in some scenarios?
I will discuss something. Yeah. So wait is your question. Yeah, wait is your question. Right. So if we throw away the boundary term, so if boundary term is gone, we just derived the Einstein equations in the absence of matter. So vacuum Einstein equations are simply that G mu nu equals to 0, right? Because boundary term doesn't contribute, and then I have to have G mu nu equals to 0. So by the way, I can contract these things by G alpha beta. So if you write G alpha beta, so what do you get here? R. And then let's say I'm in d dimensions now. I have -1/2 R, -1/2 R. And then I have G alpha beta. What is that? It would be 4 in 4 dimensions, or generally d here. And so if G alpha beta is 0, this must be also 0. The contraction of that must be also 0. So you see that if you are not in 2 dimensions, so in 2 dimensions, if d is 2, you have R minus R, and you don't learn anything. But if you are in any other dimension, then you learn that R has to be 0. Okay, so if d is not equal to 2, then the Ricci scale has to be 0. But if the Ricci scalar is 0, so this guy is 0, so the vacuum Einstein equations can also be written as R mu nu equals to 0, provided that d is not equal to 2. These are the Einstein equations in vacuum R mu nu equals to 0. Isn't this amazing? So we just derive Einstein equations so far in vacuum, but by just saying, well, R is the simplest thing I can ever consider.
And if we wanted the cosmological constant?
Yeah. You can add that as well. So you would just add, instead of R, you would add 2 lambda or something. So you would have R plus 2 lambda, or minus 2 lambda.
So into the
Yes?
does that mean that we can have known flat space-time even if we don't have any matter or energy there?
So very good. So the flat space-time would be a solution of this equation, right? So in flat space-time, I cannot have any matter which gravitates. So considering flat space and putting some matter fields on the flat space is not consistent, because these matter fields have some energy momentum, and the energy momentum would back react on the space-time and would curve the space-time. So that's an inconsistent approximation.
But in 2 dimensions, that satisfies.
Oh, I don't want to discuss in 2 dimensions. So 2 dimensions is very, very special. You can show that in 2 dimensions, actually, every metric is what? Conformally flat or something like that? Or maybe even flat. Probably conformally flat. So 2 dimensions is very, very special. Let's postpone the discussion of 2 dimensions. So if you are interested in 2-dimensional gravity, talk to Rob Mann at the University of Waterloo, who is the biggest worldwide expert on 2-dimensional gravity. you can take certain limits of the Einstein equations to 2 dimensions, which are non-vanishing, and you can even study black holes there. But typically, what people do is that they add some matter. If you add some matter, for example, scalar fields, then this is what they call gravity in 2 dimensions. But really, it's a subject which goes very, very far away. Other questions?
Isn't it supposed to be R is 0, not R mu nu is 0?
Well, if R mu nu is 0, R is also 0.
But the other way around isn't true. If R is 0...
Okay, fair enough. No, if R mu nu is 0, R is 0, and that is 0.
Yeah, but if R is 0, R mu nu is not necessarily 0, right?
But that's Einstein's equation.
Yeah, if R is 0, then G mu nu is equal to a half R is equal to R.
Is something wrong on the blackboard? No.
If R is 0, then G mu nu is equal to R mu nu, which is equal to 0 for the equations of motion.
Okay, I just want to make 2 remarks about this. So let's make 2 remarks. So if you look at our Einstein equations in vacuum, they are G mu nu equals to 0. Of course, G mu nu is a function of the metric, of the derivative of the metric, and the second derivative of the metric. So now Einstein equation is that you are setting this equal to 0. So now look at this something. We started with the action, which is already second, well, it already has second derivatives of the metric. And we end up with an equation of motion, which is also second order differential equation. This is second order. Okay, so how is this possible? So you know from your classical physics course that if you start with an action which has q dot, and q double dot, then your equations of motion will be fourth order equations of motion, right? So you have to get, so we were supposed to get here fourth order Einstein equations in the derivatives of the metric, but we didn't. So why is it true? And it's because this square root of minus g and r, g and dg and d square of g, can be actually split into 2 terms. Into a term which depends, let's call it r tilde, has nothing to do with r, g and dg. So into a term which depends only on the first derivatives of the metric, and a total derivative term r mu, which depends on g and dg. So similar to the problem which we discussed in the first tutorial in classical physics course, you can write your action which depends on q dot, and q double dot as something which depends only on q and q dot, plus a dot of something which depends on q and q dot, right? So now, of course, this thing here, if I vary just this part here, it gives me second order differential equations, and these are the Einstein equations. So this gives me Einstein equation, and this term is simply a boundary term, right? This gives me a boundary term. But this boundary term now depends on the metric, but also on its derivatives. Okay, so to kill this boundary term, I need to prescribe the metric and the derivative on the metric on the boundary. As in the same way as we had to prescribe whatever the q and q dot was on the boundary. So to kill this, need to prescribe g and dg on the boundary. But if you do it, and you have second order differential equations, and now you prescribe whatever the g is on the boundary here and there, and dg is on the boundary here and there, you are prescribing 4 conditions for second order differential equations, so there are no solutions. So then, no solutions. And that means that Einstein-Hilbert action is actually ill-posed. Posed as a variational principle. Okay, because simply, to throw away the boundary term, to throw away the term which is thrown away, actually you cannot do it because you would have to prescribe too many boundary data, and the solutions of the Einstein equations would never exist. However, people don't care, right? So they just say, well, this boundary term is simply not there. I don't care about boundary terms. I just care about whatever happens in the bulk, whatever happens inside the space-time. And so then it's this part which gives my Einstein equations. By the way, look at this split here. So this is a partial derivative, not a covariant one. And this thing here depends on g and just one derivative of g. So this cannot be a scalar because it has partial derivative. And this cannot be a scalar because it only depends on g and partial g, and there is no such scalar. Okay, so what you have to do is that you have to split the scalar here, well, not really, scalar density, into something which is not a scale and not a scalar. So this is not a covariant split. So this will be different in different coordinate systems. It's not a tensor, this one. It's not a tensor, that one. But this part gives you the Einstein equation. Yeah, there's a question.
Yeah, but you said that we don't want an action with just dependence on the metric and the first derivative because you can always go to the flat case.
Yes.
But there you're splitting in a part that is just dependent on.
Exactly. Yeah, exactly.
So?
So precisely, it's a problem, right? So this is not a covariant split, and so I can really do this split on a given in a given coordinate system. So all I'm trying to say here is that, well, forget about this split or whatever. Forget about that. So the real thing is that I start with the action which has 2 derivatives, and I end up with the field equations which have 2 derivatives. The only possibility is that something like this happens, right? So this has to happen. But if this happens, that means that the variational principle is not well posed because I have to prescribe too many boundary data. So the way to fix this is, of course, to kill this boundary term by hand. And so if you can't kill that boundary term by hand, well, that's what we did here. Or you are more sophisticated and you add to the action another boundary term which kills precisely this term. Okay, so this can be fixed. This can be fixed by adding a boundary term, a boundary term which cancels these. So on the boundary I have this, something which depends on g and dg as well, which cancels these partial derivatives of d, canceling dg terms on the boundary, and so this term was found, I don't know, what is it, maybe 70s, 80s, and it's called Gibbons-Hawking term. And again, you will discuss this term in the gravitational physics course. So all I'm saying is that the Einstein-Hilbert action is not well posed because you would have too many boundary data, but you can make it well posed provided that you add the corresponding boundary term, basically canceling the part which you don't want here, so the dg part of this term here, and the corresponding term is called Gibbons-Hawking.
So is the term you add itself a scalar?
So that term, well, it's a boundary term, but it's a scalar on the boundary. scalar on the bound.
So you've added a scalar to cancel something that's not a scalar.
Oh, well, I don't know. But I have a scalar on the boundary. I'm not canceling the whole thing here. I'm just canceling the part which depends on dg. So yeah, it's strange. But you will see it explicitly. Okay, so that was the remark number 1. Remark number 2 is actually much more practical for us. Is that we have done the variation of the Einstein-Hilbert action. And the Einstein-Hilbert action depends on the metric and second derivatives and second derivatives of the metric. So for this reason, the corresponding formalism is called second order formalism. So S Einstein-Hilbert is such that the Lagrangian, well, how do I write it? Depends on G, dg, and most importantly, d square of G. And so because you start with something, so that's called second order formalism. So you treat the action of Einstein and Hilbert as a function of G, of the metric, and then the Lagrangian density depends on up to 2 derivatives, and that's called second order formalism. So you see there's lots of fishy things going on, like we are throwing away the boundary term, which we are actually technically not allowed to throw away. So now there is a different action, which is called Palatini action, and it's called first order formalism. First order formalism, which makes things a little bit more satisfactory. And that's through the Palatini action. Okay, so now what you do is that instead of formulating that action over there as Einstein-Hilbert as a function of G, you have as Palatini, which is now a function of 2 fields, of the metric and of the connection. So you now suddenly pull out of your hand a new action where you have 2 independent fields. You have the metric G and the connection gamma. And so surprisingly, this action is the same thing as the Einstein-Hilbert action. So it's minus square root of G mu nu, R mu nu. So that's the Einstein-Hilbert, it's the richest scalar. But now look at this beauty here. So I'm saying this is a function of the metric. Well, the metric enters to the square root of determinant. It enters through this term, but actually it's not in R mu nu. The R mu nu entirely depends on the connection. So that's the fact which I was stressing when we discussed R mu nu. Is remember that you have this formula for the Riemann tensor, alpha, beta, gamma, delta. Well, what am I writing? R, alpha, beta, gamma, delta. And it was something like gamma, gamma, minus gamma, gamma, plus d gamma, minus d gamma. Okay? There was no metric whatsoever anywhere. Right? So it's simply in terms of the connection. And so in order to write down the richest scalar, I just need to contract index alpha with gamma. Right? But for contraction, I don't need a metric again. Right? So our alpha beta will also be a function of gamma only and no metric. Okay, so our alpha beta, R mu nu is a function of gamma. Yes?
In this formula, there's no dependence on derivatives of the metric. So apparently the metric is an auxiliary field.
It's not?
It's an auxiliary field.
If you want, yeah.
But
it's like a Lagrange multiplier, yeah.
the connection that if you specify that a connection has to be Levy has to be has metricity and torsion free, we get a linearity of the connection.
That's right.
With torsion free and a connection, can we get a metric under some special conditions? Because that would be what this seems to.
Okay, so I'll tell you what the argument now is. So and then that partially answers your question. So now we have this action here. It's an action of two fields. So I can vary it with respect to the metric. The statement is that if I vary the action with respect to the metric as Palatini, well, all you have to vary is square root of g and g mu nu, and this you leave untouched. But if you remember what we were doing here, and what gave our Einstein equations, is that we vary square root of g and we vary g mu nu, right? So this immediately gives you the Einstein equations. Einstein equation g mu nu equals to 0. Okay? So if you vary this action, you don't have to care about this ugly term here, because simply, it's a function of gamma, and it's a spectator in this variation. But then you also have to vary with respect to gamma of S Palatini. Okay, I have another variation, and that actually tells me that gamma is the Christoffel connection. So I don't know if that answers your question, but partly it should. So the statement is, if I now vary this action with respect to Christoffel, with respect to the connection, then I'll find the formula that this connection is given by my familiar formula between the metric and the Christoffel symbol. Okay, so actually you can derive that from this action that your gamma is a Christoffel connection. We can discuss if this doesn't answer your question. And okay, very good. So that's a second order formalism. We had the second order, which was the painful through the two derivatives. This is the first order. And then, of course, there's something in between. So there is 1.5 order formalism, which Gary Gibbons showed me. And it's just one big cheat. So it's 1.5 order formalism. And so that idea is that, well, I use the Palatini action, which depends on G and gamma. But I know that all I have to do, so use as Palatini, but I know that all I have to do to get the Einstein equations is just to vary that with respect to the metric. As Palatini equals to 0 gives me G mu nu equals to 0. And then everybody knows that if I vary with respect to the connection, I get the Christoffel connection. Okay, so the statement is I can only do variation with respect to the metric here, and then use the fact that we have use Christoffel connection, which we know is in GR, right? So basically you don't have to do the second variation because you know the result. Okay, so that's what Gary Gibbons advised me to do. And this is really, this is well-posed thing, right? So here, it's the simplest thing ever you can do. All right, are there any questions?
What about other scalars you can construct with Riemann tensors?
Aha, that's a perfect question to end up this lecture. So what do you think?
I think they're going to give you higher order derivatives of the metric.
Uh-huh.
And that's not cool, but anyway, I don't know.
So This is a very, very good question. So now going in the steps of Born and Infeld, we might think that we can actually do any function of the Ricci scalar. But actually, that's not the only scalar. So okay, so which scalars I have? So which scalars I have? So the simplest one is the Ricci scalar. But another scalar I can write down, if I don't insist that it's linear, I can write down r mu nu. Okay, that's another scalar I can form. Or I can form scalar r mu nu kappa lambda, r mu nu kappa lambda. That's another scalar, and that's just considering the scalars, or I have r squared. So this would be linear scalars in the curvature. Then I would have quadratic scalars in curvature, which are these. But I could also consider things like nabla mu r, and so on. So you can also consider derivatives of the scalars, and so on.
And Hodge of the Riemann tensor.
And yeah, exactly. You know, all these things I can consider. And then you can write down an action which depends. So L, which is a function of all these scalars, function of all scalars. Of course, the problem is, if I do this, then all these scalars have already two derivatives of the metric in them, right? So they already the Ricci scalar does. But the Ricci scalar is very special. Is it still here? Probably not. Oh, it is still here. The Ricci scalar is very special that I can decompose it into these two things. But if I take any of these higher, order scalars, it won't be true. So in general, if you write down the equations of motion for this, then you get higher order equations of motion. And you typically don't want that because these are ill-defined. So nevertheless, people do it. And then they are typically happy if the equations of these higher order equations of motion are nice on some nice solutions, for example, on vacuum or on spherical symmetric spacetime. So people, for example, devise something which is called, how is it called? Topological gravity or quasi-topological gravity. So quasi-topological gravity is simply a gravity where you write down the Lagrangian, which depends on some of these beasts. But and so it gives fourth order equations of motion in general. But if you consider spherical symmetric solutions, the equations suddenly become, for some miraculous reason, second order, and you can solve them easily. Okay, so on some special solutions, this may reduce to something nice, and so then people consider these things. So then you may be asking, is Einstein theory the most general theory which gives you the second order equations of motion on any solution? And the statement is no. Well, yes and no. It's true in 4 dimensions. So is a uniqueness result. Shown by Lovelock that if you are in 4 dimensions, in 4D, and you want second order equations of motion, then really what you can do is this thing here. Well, I can also add this -2 lambda, but it's not important. Okay, so this is the only thing. If you are in higher dimensions, you have more possibilities, and you can actually combine these terms together. So you can add, some of these higher curvature terms, but you have to prescribe the precise coefficients in front of these things. And so the correction to this Einstein-Hilbert term will be given in terms of the topological densities. So they are topological in 4 dimensions, but in higher dimensions they become things. And then you derive things like Gauss-Bonnet gravity or Lovelock gravity or whatever. So this is in 4D. In higher D, you have Lovelock gravities. And so all these things have second order differential equations, but then you have to be very, very careful what type of Lagrangian you write down. And there is a unique prescription of what you have to do with these scalars to form your Lagrangian density so that it gives you second order differential equation. Other questions?
Lower dimensions.
You really like lower dimensions? I don't know. So certainly in 3 dimensions, as we will see tomorrow, the gravity does not propagate. So if you are in vacuum, you don't have any gravitational waves and stuff like that. There's no any degrees of freedom already in 3 dimensions. So gravity in 4 dimensions is pretty unique and special. Yeah, if you go into 2 dimensions, it's even more screwed up. But in 3 dimensions, gravity. So that's why, for example, cannot have black holes in 3 dimensions if you are in vacuum. And so maybe you heard about BTZ black holes, which are black holes, but you have to have some matter. And so the simplest matter is the cosmological constant. So in 3 dimensions, you can have black holes, but they have to be with cosmological constant black holes. Other questions?
So this Lovelock thing tells you that there's no modified gravity. I don't understand that.
Well, I'm just saying, if you start adding these things, so for example, the favorite thing in cosmology to explain galaxy rotation curves and dark matter and stuff like that you just put any f of r, so you're screwed up. So this theory is ill-defined. It has its higher order equations of motion. You have ghosts. You have all the problems you can imagine. Maybe it's not even well posed like initial value problem. I don't know that, but maybe it's even that. But people don't care. They just they are desperate, right? They're trying to explain things by theories which do not make any sense, right? But anyway, yeah. All right. So let's discuss matter tomorrow.